Our speaker today for MongoDB is Asya Kamsky, and Asya spent about 20 years in the high-tech industry, mostly doing relational database stuff, back-end e-commerce, securities, back-end systems, and fell in love with MongoDB a few years ago and ended up working at 10gen. So without further ado, I'd like to introduce Asya Kamsky from 10gen.
All right. Look at that. Good morning. I'm an engineer, so I'm not a 9 a.m. person either, so I feel your pain. Now, I can't see you guys too well, but I'm going to try asking a few questions anyway. You can raise your hand, and I'll hopefully see a sea of palms. How many of you have actually used MongoDB, have tried it, or actually use it at your company? Wow, it's quite a few. Of those folks who have not used MongoDB, how many have used relational databases, or any databases? Pretty much everybody, right? Yeah, so I'm going to start kind of way at the beginning. I'm going to assume that there's a few people here that were not raising their hand, not because they're too shy, but because they actually haven't tried Mongo and haven't really worked that much with databases, maybe even. But I mainly want to make sure that we're kind of all on the same page and understand why it was that MongoDB came around, right? What was the need? There was already lots of databases. Why did we need another one, especially one that's so different? Hello. Hello, computer. So, a little bit of history. Long time ago in a galaxy far away, storage was really, really expensive, and somebody invented this normalized data model. And the cool thing about normalized data model was every piece of data was stored once, and then you could kind of reference it, and you had your master database, and you could write lots of different applications that all kind of pulled data from that one central place. The application didn't actually get to decide how to store the data. The data already existed. The application just decided how they were going to use it. So relational databases were a big hit. I spent a lot of time working with them. I actually worked for a relational database company once upon a time. I've worked with pretty much most of the major ones and a few of the open source ones. But then in the 90s, things began to change a bit. And in the late 90s, if any of you were already working back then, all of 15 years ago, you probably were familiar then with the problem that happens when you have a lot of web traffic that's increasing, and you go, oh cool, we've got these load balancers now, we're going to throw them all in front and balance lots of load between them. And they're all talking to the app server or app servers, because when you overload an app server, you can just have more of them. The problem was they were all talking to a single big relational database in the back that the only way you could scale was put more memory in, add more CPUs, add bigger, faster disks, repeat until you run out of money. It was very difficult to scale it the same way that you were scaling everything else. What added to the problem was the popularity and the rise of social media, where people were no longer just consumers of information. Because if you're just a consumer of information, the information can be very easily replicated across the web, right? I can basically push my content to be cached all over, and there's a lot of companies that will help you do that. But with social media, every end user was suddenly generating content as well as consuming it. Well, that's tricky. Now you have to somehow set up things to distribute or scale so that everybody can't just read from it, but they can also write to it. Oh, and then they also want to be able to read back what they wrote, which is also kind of tricky. E-commerce, of course, had existed already, but it really became very widely accepted. And again, in e-commerce, some things you can easily cache, right? Your product catalog doesn't change very often, but when people are placing orders, well, that's something you have to write and make it available to people to check on their offer right away. The amount of data that we were collecting was growing tremendously, right? We used to talk about gigabytes like they were a lot, and now you just have a gigabyte. But you have terabytes? Huh, we have petabytes. Oh yeah, we have whatever the next one is. I don't know what it is, but that's what we have, right? What can we do with it though, right? On the other hand, hardware has gotten a lot cheaper. So you would think that if we could figure out what to do with it, it wouldn't cost as much, right? Because there's a lot more cheap hardware. So we need to scale. How do we scale? So another thing to consider is, I didn't even go back to the 70s when relational databases were first created, because you never know whether you can trust Wikipedia with things like, how much the disk used to cost back in 1975. But I dig around, typical computer back in 85, back in 95. And then just for laughs, I decided for last year to look at my phone instead of a computer. And I realized that my phone was significantly more powerful than probably the first mainframe I ever used in school. So my college had some big IBM mainframe. And yeah, my phone probably has like an order of magnitude more computing power than that entire mainframe. So, but just kidding, so we don't actually want to do processing on our phones. Although phones are very effective clients, and we can push more work onto the client, right? And the rise of mobile is driving a lot of changes in how we make software, how we think of interacting with a website or a company, right? The other thing that changed is, just near 15, 17 years ago, if somebody said something about the computing cloud, you'd be like, I don't know. And if they said it 10 years ago, you'd be like, oh yeah, that whole software as a service, that's never going to take off. Everybody's talking about it, that's not going to happen, right? Well, that's happening now. So how is this all affecting developers? Now, how many of you guys are developers? Okay, of those of you who didn't raise your hand, have you ever been a developer? Managers of developers, maybe? A few? So something that's very popular with developers now is the agile methodology. And I've met a few people who go, oh yeah, agile, that's why we have these short development cycles now. Never enough time to do anything. And I go, I think you have it backwards, right? Agile development methodology didn't bring us short development cycles. It was the fact that there was demand to constantly change things, right? The requirements themselves were iterating so fast. Agile simply recognized and accepted the fact that it's always going to be the case that we won't know all the requirements up front. It's always going to be the case that we're going to have to iterate as new requirements come up, right? And so by saying, okay, let's go with it, we understand now we're not going to create something and say, okay, it's done. This is good for the next 2 years. And if you have new requirements, we're going to make another 2-year plan, right? Because your competitors basically eat your lunch when you do that. So you want to have flexibility at design time. And this is probably one of the places where the whole relational database paradigm became a big pain, right? I mean, there's the whole scalability thing, right? That's operations problem, right? For developers, we don't care about that. But relational schema, and I've done this, right, because I've been the data architect. I've come up with what I thought was great normalized schema, given the data we were going to be saving. But then working for a small company, I put on my developer hat and I code, and then we push it live, and then I put on my DBA hat and I yell at myself. How could you do that? I can never scale this. What are you thinking? I'm thinking I didn't know what the requirements were going to be, right? So relational schema, it's very hard to evolve it, right? You either try to be really flexible up front, in which case it's very hard to be performant, or you try to design something that will perform well, but then will be flexible for slightly different use cases or different ways of accessing the data. So what did we do as developers, right? Well, when things got started, we had our normalized model, and things was great. And then, performance is kind of suffering. When we're joining these tables, it always takes forever. Let's denormalize some data. So we would denormalize data to structure it more like what we needed to access in the application. And then you go, you know what, we're going to need to stop using joins, because whenever you do a thing that joins those ginormous tables together, it's bad. And you go, well, no, how about we just build like an in-memory cache? So we just hit the database once at the beginning when the server started up, and then we'll cache the information so it'll be in memory, and boom, boom, boom. And then eventually you say, okay, we've just reached the limit of how much data we can store in this database. So let's have a separate database for this part of the application and that part of the application. So we're essentially partitioning on the application layer where the data lives. Suddenly we're thinking these great relational databases, which absolutely have phenomenally mature, strong features, but if we're working against those features, if we're working in a way that's not using them, we're trying to make them do what they're not good at. And I, by the way, spent my share of time doing that. By the way, what happens in the operations world is, when they first launched the application, they got the server, they got the sizing, and then as the demand grows, they're forced to upgrade the server, get a bigger server. The migrations for them are painful, and the costs basically are not very linear. If you've ever priced the really, really high-end servers, or a server that's twice as powerful is going to cost about 20 times as much, right? So we say, okay, need a new database. We want to solve some of these problems, right? We want to be able to scale it horizontally. And what does horizontal scaling mean? Well, it just says, if you have a relatively inexpensive machine, you can get like 10 times as many machines and hopefully have close to 10x the capacity. You want to be able to run it anywhere. And what that means is the cloud. The cloud. Who uses the cloud here? I use the cloud. It's so simple. Like, you can get a tiny instance or whatever micro instance on Amazon. It's free. It's like, I know what they're thinking, that I'm going to put a mission critical app on it and then it's going to grow and then I'm going to have to spend hundreds of thousands of dollars with them. But I just use it like for testing stuff. But still, I'm getting dependent on it, and I'm used to the fact that I no longer have to wait for IT to provision something, or I don't have to go to the store to actually buy a server. Flexible data model, that's something I'm going to talk about a lot. So actually, most of you probably know what I mean by that, right? Is not knowing today what data we're going to need to store tomorrow. We want to develop faster. I know the whole work smarter, not harder thing, but the fact is, in order to deliver features quickly, we need to have as few obstacles as possible to getting essentially to the next level of functionality with any application. And of course, everybody wants it to be free or cheap, or at least not super expensive, not just when you start, but also to maintain. So essentially what happens is the database world kind of got partitioned into three very separate types of database engines, right? There's the traditional relational online transaction processing operational databases, right? For quite a while, maybe from the mid-90s or late 90s, there was a very distinct category of databases for business intelligence or OLAP type processing, right? The analytical business intelligence. You guys know what I'm talking about, right? Long-running queries, you transform the data into different format. It maybe has different best practices for schema than OLTP. And it's good for some things, but again, doesn't quite answer the whole new data paradigm. So the NoSQL, some say it means no SQL, some say it's not only SQL. I just say it's non-relational. It's a new category of products, and there's actually quite a few of them there, right? We have the key value stores and columnar stores and graph databases, and then document databases. Now, some of these are very specialized. Some of these are more general. I'm going to talk about document databases because, well, first of all, that's what MongoDB is, and that's why I love it. And second of all, because it's one that's very general. It's not for a narrow, specific purpose. And it was really meant to solve the problem that relational databases hadn't been designed to work with very well, because 30 years ago, nobody really thought about development the way we think of it now. So in comes MongoDB. Now, the founders of 10gen and co-authors, creators of MongoDB, they worked at places like DoubleClick. Actually, one of them, Dwight Merriman, was one of the co-founders of DoubleClick. If you guys know what DoubleClick is, if you're ever surfing around and you look at the name resolution, sometimes you'll actually see the ad stuff still reference the DoubleClick domain. DoubleClick served up ads, and Google bought them in like the early 2000s, still serves up ads. At one point, they had to serve over 500,000 ads per second. And these were not cached ads. These were targeted ads based on a query that was customized to the viewer based on whatever it was they had done. And they had to solve this problem of trying to scale a big relational database in a way that would scale with the number of users. After Dwight and Elliot, our co-founders, left DoubleClick. Elliot founded ShopWiki. Dwight founded Guild Group, BusinessInsider.com, a few other companies. And they always seemed to have that same problem. So they got back together and they said, actually, they didn't say let's write a database. They said let's write an app platform engine, but we'll write our own database for it rather than using an existing one, so we won't have these problems that we always had before. Funny thing happened is nobody was really interested in the app platform, but everybody said, oh, but I've had the exact same problem with my database, so I would like that database, that when that's ready, I would love to use it. So they listened, they stopped working on the app platform and concentrated on the database, and that's what became MongoDB. Mongo, those who don't know, supposedly short for humongous, because the idea was, oh, it's going to be able to scale humongously. But the real huge benefit that people noticed immediately was how easy it was to work with, how easy it was to get started with. So their goal was they wanted to do high performance, they wanted it to be horizontally scalable, fully consistent. I'm going to talk about that a little bit more later when we talk about replication, but fully consistent, strong consistency basically means you can read your own writes. If you write something, that you can always immediately read it. And general purpose. So something like a graph database is specifically designed to work on graphs, right? Nodes and edges and complex queries about relationships between them. General purpose database is designed to work with any case, right? So 80% of the time it's going to be great. 20% of the time maybe there's a more specific engine or type of database that you could use for an exact use case. You could do it in the document database because it's flexible and documents can represent pretty much any entities. But the goal was to make it a general purpose data store, kind of like the way we've been using relational databases. So there we go, we have MongoDB. Part of designing MongoDB was, well, how are we going to make it easy for people to try it? Here we are, it's 2007, 2008, late to the party. There's already lots of data store options out there. So one decision was, let's make it available under an open source license. Anybody can just download and try it. And two is, let's write drivers so the developers can communicate with the database in language that they're already familiar with, language which they already understand, so they don't have to be like, oh, I already know SQL, now I have to learn a new query language. Instead, they'd be like, oh, I'm already working with objects, hashes, associative arrays, dictionaries, whatever. The objects just map to documents in my database, and it'll be easy to work with. So that was kind of the chart. If you think about relational databases having a lot of functionality, which of course they do, but being very hard to scale across many different servers and regions and data centers, you think of something like an in-memory key value store as being exactly the opposite. It's super fast and performant, but for a very narrow range of functionality, right? You can store something by key really fast. You can get it back by key really fast. It may have some relatively small amount of additional functionality, right? But you can't do with it what you can do with an RDBMS. You can't do ad hoc querying. You can't index data by anything other than the key, right? You can't have flexible, meaningful structures. It's just a key and a blob that represents a value, right? So the goal was, well, what is it that we have to give up from the RDBMS side to give us the scalability and performance that approaches, key value store? So you don't have to give up all the rich functionality, just a few things, right? So you get the great performance and you'll get a lot of functionality, so it'll still be very, very useful for general development. So that was the goal. That was kind of the philosophy of design behind it. And the approach they took was, it was going to be a document-oriented database. Now, how many of you guys here know what JSON is? And I'll tell you, those of you who didn't raise your hand, you will after today, because pretty much every topic we cover today is going to deal with JavaScript, JSON, related to that kind of format, right? So JavaScript object notation, these JavaScript objects, they've sort of become a de facto default format that like 15 years ago we thought XML was going to be, right? things going from like the website to the back end. This is a very common format for data to be in. Why? Because it's flexible, right? It can express a lot of richness in terms of relationship between different parts of the entity. Now, Mongo does not actually store JSON documents. It serializes them into BSON, which is the binary form of JSON. And that's because, well, first of all, binary is more compact than string notation. The other thing is, of course, JavaScript doesn't support all the different data types that you might want to have in your database, right? You're writing a real application. Every number you use might not be a float, which, in JavaScript it tends to be. And you might want to have special data types. You might want to store, binary data, image files, different types of numbers, strings, dates, etc. And you want it to be dynamic, which of course JSON is, right? Every document can be slightly different. The design was to have the scalable architecture where you'd be able to add additional servers to get more throughput. There's a feature I'll mention in more detail called auto sharding. There's high availability via replication and failover. And Mongo uses memory mapped files, which is something that allows it to be very fast for data that you access most frequently. It's durable, and durable just means that if you make a write and that write is successful and the machine crashes, that write will be restored when the server comes back up, right? So it's written into a write-ahead transaction log, essentially. It has strong consistency. You can read your own writes. Now, you have an option. You could choose to use eventual consistency, right, which means that you'll get that data eventually, but not necessarily immediately. But that's an option, right? Mongo supports many different types of indexes. So you can index primary keys, obviously, but you can also index various secondary characteristics, including indexing arrays, indexing embedded documents, two-dimensional indexes. So geospatial queries are supported. It's built right in. There's an ad hoc query language. Can it do everything SQL can do? I think so. It can actually do a lot of things SQL can't do. So there are a lot of operators that are built in to make it easier to do certain operations, which, as a developer, I really appreciate. Ability to aggregate large, complex data, and ability to write map-reduce jobs, which is a more sophisticated way of writing analysis. Involves actually writing JavaScript. We won't go into the detail of that here. By the way, I don't have a clock. I'm trying to keep an eye on the time. Is there a... All right. Cool. I don't want to run too over, but I'll run over if you guys look like you're having fun. So JSON, right, rich data model. This is an example of a JSON document, right? There's some key value pairs inside of curly braces, and they represent name of a key and a value, right? So this document says there's an author key, and the value of it is Elliot. That's a string, right? There's a date, and as a value, it's going to generate a date. That just generates the date representing the current time. There'll be some text. And then there's tags, which has square brackets. For those who don't know, that's an array. I'll talk in a little bit more detail. In Mongo, the query language, when you invoke it from the shell, looks something like that statement there. You say database, name of the collection is post. Collections are just like tables. So if you work with relational databases, you're already kind of familiar with how it works. Say save or insert. Save is kind of like a insert if it's not there, overwrite it with this if it is. Very handy option, right? Flexible, and I'll tell you how it works with, how it helps with data locality. So let's say that you want to write, I don't know, a blogging website, right? It's a good exercise, it's pretty straightforward. Let's say you let users register. They'll post, thank you. They'll post blog entries, right? Or if you're registered, you can comment on other people's entries, right? Now, you don't know what other features you might want to have in the future, right? But you say, okay, well, I'll implement tagging up front so that people can immediately search for topics they're interested in, and maybe I'll let people vote in the future, because that way, well, maybe I can show the most popular blog posts when they're searching for something. You don't really know what's going to be required, but you're kind of trying to keep these things in mind. In relational database, you have some probably massive schema. I simplified it quite a lot. You'll probably need a table for users, posts, comments, right, that are associated with authors and posts. If you want to tag things, well, because each post can have many tags, you have to put it into a separate table, right? It's got to represent a many-to-many relationship. This is kind of one of the things that's always been a pain for me in the relational world, especially when you don't know in advance all the attributes that you're going to want to represent, right? So how I might do this in MongoDB and JSON? Well, first of all, I don't have to declare a schema up front. I can just start saving documents. And I know each document is going to have an ID. So ID is a primary key. You have to have an underscore ID field in every document. If you don't provide one, then the system will generate one for you. And it's of type object ID. It actually has meaning. Those of you who've worked with Mongo know it encodes things like creation date and a few other things, so you can actually use it for useful things. It's not just a random key. I got a title, date when this was published. For author, now there's going to be another collection, right, representing users. And of course, I'm going to store stuff there that I don't usually need, like the author's password and their email address that they might not be exposing to the world. But certain other things, rather than referencing to them by a foreign key or an ID, I kind of would like to denormalize into the blog post. Because to display a blog post, I don't want to have to go to another collection. I can just store an embedded document that says the author's name is Asya Kamsky and the author's username is Asya. Because you know what? I have an invariant, the username can't change. So I'm not worried about denormalizing that because, well, it's not going to change. Plus, it works really well as a foreign key because you can then look things up by username since they're required to be unique. My name, well, my name's not going to change. Somebody's name, well, how often is it going to change during the duration of your blog site? Not very common, right? Text, well, Mongo documents are limited to 16 megabytes, and I'm told that that's like War and Peace a couple of times over. So you can just have the text right there in the document. Tags. So I can store an array of values. And the beauty of that is that a tag can have many different values, and you can search by tag, and you can index tags. So indexing an array field is kind of the same as indexing a regular field. So you say, I want to ensure index is a Mongo query language command for create an index if it doesn't exist, and if it does exist, then it's a no-op. So I say ensure there's an index on tags, and it creates a B tree. So if you've worked with relational databases indexes, it's exactly the same format. You already know how Mongo indexes work. And now when you do a select, which in Mongo is called find, you say tag news, and it uses an index to find all the documents that somewhere in the array have a tag that's exactly news. Well, that's pretty cool. Actually, it's pretty basic. Neat thing, you can do an explain, and this is just like looking at a query plan in SQL, right? When tuning things, seeing if you have optimal indexes. Same thing, tells you if an index is being used, what type of index it is, how many objects did we have to look at before we found the number that we want to return. So you're thinking probably, yeah, it's just like with relational databases, right? It might be fast up front when the data amount is small, but as it grows, you still have to have your indexing strategy, right? You have to figure out how to structure your schema, because flexible schema does not mean schema-free. I know some people say schema-free. It's not schema-free. Every document actually describes its own schema quite accurately. But if you put every document in the same collection, you're going to have to examine every document to find out what the schema of it is, right? So now you say, okay, I'm going to implement voting now. And I'm a very clever developer. I'm not letting any users get past me with any sneaky things. I'll make sure that the same voter can't vote on a post more than once, because you know they would, right? My blog post is the best. I'm going to vote using 3 different terminals or a script. So instead of say you have to be logged in to vote, and when you vote, I'm going to add your name to a voters array so that if you've already voted, I won't add you again. Well, how do you make sure that the voters array is always in sync with the votes, and that if somebody's trying to vote at the same exact moment twice, that they don't sneak in there? Well, luckily, the way updates work in Mongo is you specify the document you want to update, right? So that's the query. That's the equivalent of SQL, update something set where something, 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 right? So there's the where clause is the query. So I say, update this blog post, ID such and such, but second part of my condition is going to be if the voter's name is not already in the voters array. And then the update is going to be to increment the votes field and to push or add that voter's user ID to the array. Atomicity of this statement is guaranteed by the system. What that means is you don't have to worry about a race condition between two threads where one of them says, okay, I see something to update, and the other one says, oh, I see something to update. And then they both make the same update twice. You don't have to worry about that because the system guarantees that the statement as a whole is atomic, meaning it happens as a single unit. Now, updating multiple fields in a single update is also guaranteed to be atomic. So you don't have to worry about something seeing a document being half updated, right, where I've pushed ASIA to the voters array, but I haven't yet incremented votes. By the way, $inc is increment by 1 votes, right? So when it executes, I have another element in the array. I have votes incremented. Anybody think of why we would want to keep both, even though we can always figure out the number of votes from the length of the array? Let's say you are. Yeah, well, not really, because you can pull the voter's name off of the array, right, and then now you see what the length of the array is again, right? How about if you, remember I said you might want to order things by most popular items first? Wouldn't you want to include that in an index? Right? If you're calculating every time how many votes each field has, you can't very well index that, right? That's not very performant, right? So we choose to denormalize, right, or keep track both of the number as well as the number, the actual voters plus the total number that adds up to, so that we can maybe index votes to make it faster to sort by it, right? All right, advanced stuff. Comments. I'm allowing comments. Where do I want to store them? So now the interesting thing in Mongo is flexible schema means you have a choice. You could store it in the document itself. Each document might have an array of embedded documents. Each element is itself a JSON document. That's pretty cool. You can even index by things that are embedded, just like you can query by things that are embedded. So I say, okay, comment the by field. So comments.by refers to, inside of the comments array, the field by comment. Index the authors of the comments. I'm thinking that's a good plan for when somebody logs in and it says, here's your last 10 blog posts, and here's the last 10 blog posts where you're involved in the discussion or something like that, right? There's the query that says, show me all the blog posts that have comments by this particular author. But in Mongo, you have flexibility. You could store comments in a separate collection that references the blog post. Now, I say reference. I'm very careful not to use the term foreign key or joins, because the database does not provide any built-in join functionality. The joining or referencing would have to be understood by your application. So Mongo allows you to have these rich, complex structures, or it lets you put things into separate collections, but it doesn't give you what we call joins in a relational database table. Yes?
Would you say since the application itself understands the join relationship that the database itself is tailored toward a particular application, not necessarily a database to support an integration database to support all of the systems?
So I'm going to kind of repeat the question, rephrasing it a little bit. So because the application has to understand the relationship of the data, Would I then say that Mongo is a better database or data store for a particular application as opposed to a database or data store that's system-wide and allows access to its data by many different systems? Yes, I would definitely say that, because the way you get best performance and best usability from Mongo is if you tailor the way you structure the data to the way your application needs to access the data, whether it be reading or writing, including putting things together if you get them always together, or splitting them up if it's more performant and makes more sense to split them up. And this makes it, certainly to the part of my brain that spent over a dozen years normalizing schema, it makes it a really weird animal, because you go, but what if I want to access data differently tomorrow? Like, well, what if I have a different application? If I have the same application, I evolve my schema, right? I evolve it to match the application requirements. But really, the reason, and if you talk to developers who've developed with Mongo and love it, the reason they love it is they're thinking about their application. Mongo is like this thing that they get to persist the data to very fast, and they get the data back out very fast. They're not thinking, how do I structure this data for mine and everybody else's application? So it is a very different mindset, especially early on. It makes it very easy to get started, very easy to prototype different approaches. It doesn't make it a good candidate at the beginning to say, we're going to make that the storage system for every application, because now you got to have everybody agree. And of course, they're never going to agree. They're going to be, I want my application to have the best, fastest access, right? So that's, we'll talk about that a little bit after lunch. So, before we go on to the next point, one thing that you can do in Mongo is, dynamic, flexible, caters to the exact needs of your application. You can actually do both. You can say, I'm going to save the first 3 comments into the blog post itself, and I'm going to store the rest of them in a separate collection. And you might want to do that because you go, when somebody loads a blog post, I want that to be fast. But I'm not going to show them every comment that there is. If somebody makes a controversial blog post about, is Lady Gaga better than Justin Bieber, and 50,000 crazy 12-year-olds, no offense, any 12-year-olds, show up there to argue this point, you don't want all that to be embedded in the blog post. Not just because it's going to exceed the maximum 16 megabyte size, it's because you don't need that information when you first show the blog post, right? If you go to shop at Amazon and you look at a product, do you see every review that there is? No, you see like the ones that were voted most useful. Most helpful positive review, most helpful negative review. Now if you click, show me the rest of them, now it's got time to get more data, right? So this, again, is thinking about what your application needs first and tailoring the schema to that. Essentially, the schema follows your application requirements, not the other way around. Very different, definitely very different. But look what it gains you. At least until we all have SSDs, maybe even then, right? We have these spinning drives. Seeks are really, really expensive. The actual reads are relatively cheap compared to seeking to exactly what you want to read on the drive. If you're seeking to where a whole bunch of different database tables are stored in order to reassemble an object that has been stored or normalized to many different places, right? You're making multiple seeks. Even before you start assembling the object back in memory to return to the application on the database level, it has to access multiple places on disk. And of course, all these places are indexed, which means you also have to access where the indexes are. In Mongo, each document is stored as a single unit. And this is why tailoring how the documents are structured to your application requirements means that even if the document is not in RAM, you only have to seek once in order to read that document or in order to write it. Now, the other thing is, in relational databases, because an object can be in many different places, you have to have transactions. You have to be able to say, start transaction, write to every table to represent the change to something, commit transaction. Well, in Mongo, you don't have transactions, but operations on a document are guaranteed to be transactional or atomic, kind of like auto-commit on an update to a document, which means structuring things so you're saving things only once gives you the equivalent of either all of this save will persist or none of it will persist. Make sense? Hopefully. So that's the data locality. A couple of other things that Mongo has, well, in-place updates I actually did mention, right? Some key value stores actually don't let you update the keys. You can append them, you can find them, and if you want to update them, it'll like mark the old one deleted and append the new one or something like that, or it'll version it. In Mongo, we can actually update in place just like relational databases do, which makes it quite a bit faster. The other thing it does is in-memory caching. I'm not going to go into detail on this, although if you're curious about the details, find me at lunch or during one of the breaks. But basically, Mongo delegates to the operating system the swapping in of pages that are being accessed. And magically, as if by magic, but really through the hard work of people who implement the operating system code, we end up with things that we access most frequently pinned into RAM. So usually that'll be your indexes and what we call the working set, which is your documents that are accessed most frequently, which definitely speeds up access significantly. Some of the other stuff is more operational. I'll walk through that real quickly. We'll talk a little bit more about that in the afternoon, because this is why Mongo can be easy or hard to sell to operations team, depending on whether they understand the benefits of its design and architecture or not. So high availability and scalability is achieved via replication and sharding. So replication is when you have lots of machines that have exactly the same data on them. That's how you get your high availability, automatic failover, disaster recovery, extra copies of your data for special purposes. Sharding is when you have many of those, we call them replica sets, for read and write scaling, where you partition your data across them in such a way that it splits up the load evenly, but through the magic of the drivers and some of the internal architecture of Mongo, your application doesn't actually have to know. Is it talking to a single server? Is it talking to a replica set? Or is it talking to a sharded cluster? If your application interacts with it, the node or the database or the cluster the exact same way, it creates a situation where operational changes don't require rewriting parts of the application, pushing a new version, or making any other changes like that. So high availability. In my mind, that means the application doesn't have to schedule downtime. And I don't know how many of you have used some traditional master-slave replication. Something that wakes a DBA up in the middle of the night via a page so that they have to log in to promote a secondary to be the primary, I don't consider that high availability, because I've been that DBA and carried that pager. Automatic failover is when the primary fails, one of the secondaries steps up automatically to become the new primary. The DBA comes in the morning and fixes whatever the hardware problem was that failed. To me, that's much more highly available and operations friendly. Gives you data redundancy. If you place one of your replica sets nodes in a separate physical location, it actually gives you disaster recovery copy. We satisfy some legal requirements. Again, it's transparent to the application, although application can take advantage of some of the features of replica sets. This also allows operations folks to do maintenance without any downtime. So imagine that you need to upgrade every version of MongoDB to a new version, or you need to apply a patch on the operating system and then restart every machine. What if you could do it on each secondary in turn, and when they were all done, you just ask the primary to step down, let somebody else step up as the new primary, and then upgrade that last machine? Well, if the application automatically knows how to switch from the old primary to the new primary, there's no downtime. And that's exactly how that works, right? So in a replica set, there are n servers. I use 3 a lot of times in pictures. Sometimes I use 5. Notice I always use odd numbers. Odd numbers are good for voting. Voting is how we elect a new primary. Only one of them can be a primary at the same time. Now, this is what allows Mongo to be a strong consistency system. We can only accept writes on one node in a replica set. Those writes are then replicated to all the secondaries asynchronously. If we took writes on more than one node, we might end up with a conflict. We might violate a unique constraint. We have no mechanism to resolve, oh, we took these two writes, which one of them is the real one, right? So architecturally, Mongo is structured to never have more than one primary in any given replica set. In other words, for a particular subset of data. All the writes go to that primary, all the reads go to that primary. Notice that means the reads can always read something that's just been written. Now, an application can optionally specify that a read should go to a secondary. There can be a couple of very excellent use cases for doing that. General read scalability is not one of them, but decreasing the latency of reads when you can tolerate slightly stale data, right? Running long-running analytical historical reports against a secondary, right? That's another great use case. Automatic failover, automatic recovery. So if a primary fails, another one takes over. When the original machine is restored, it catches up, rejoins the set. Looks something like this. Now, application is talking to the replica set through the driver, and all the drivers that are maintained by Tengen are fully replica set aware. What that means is they know they're talking to a replica set because they can say to a server, hey, are you part of a replica set? Tell me the other nodes that are here with you, and starts talking to all of them. So if it loses a connection to a primary, it immediately polls the rest of the members and says, hey, which one of you guys is taking over as the new primary? Gets back the result, and it will now route all the read and write requests to the new primary. That's pretty cool. DBA comes in the next morning and says, darn, somebody tripped over the network cable again and plugs back in the network cable because the primary actually never went away. It just couldn't talk to the rest of the world. Now the primary, former primary, now comes back up as a secondary, rejoins the set, says, what did I miss? Applies all those things it missed to itself. And when it catches up, you can see that the replica isn't back in the original configuration of one primary and two secondaries. It's a different primary, but they're all equal. Unless, of course, the DBA configures one of them to always be preferentially a primary, which they can do, which is why operations folks still need to spend time thinking about how they want to lay things out. But after that, hopefully, it's all automatic. Okay, so that's replica sets, cool. We got all this stuff. What about that horizontal scaling thing? So sharding is just a fancy word for partitioning. So what we want to do is we want to say, okay, I currently have one system. If I have two systems, I want to be able to split my data between them in a way that's transparent to the application, but that evenly splits the load between them. And if I can figure out how to do that, I can just keep adding more replica sets to my configuration as my popularity skyrockets and I become as rich and famous as Google or Amazon, let's say. So the idea, and the Mongo supports range-based partitioning, where you specify along which variable, along which axis you want to partition your data. Some NoSQL systems only support ring partitioning or hash partitioning. That's actually an option in 2.4, which is the new version of Mongo that's coming out next week. Range partitioning allows you to have more power over how your reads and writes are going to be distributed in the system. Once you tell it how you want to partition things, though, the actual splitting of data and balancing it across the shards is automatically handled by the system. So, notwithstanding my inferior PowerPoint animation skills, instead of one replica set, you might now have 4. So this represents a 4-shard system. Each shard is still a primary and 2 secondaries, and that's because you still want to have your high availability, right? If one machine fails, you want a secondary for that set to take over automatically. Well, now how does your application know where to send its reads and writes? Well, each shard has about 1/4 of the data. It's not going to be like straightforward like a continuous range, but it's going to have chunks of sub-ranges. And there's a process that the application talks to, which from the point of view of the application looks just like a Mongo server. But under the hood, it's actually the special sharding router, which pretends to the application that it's a regular server, But then it turns around and it redirects the queries, the reads and the writes, to the appropriate shard based on where each range of data lives. Then it assembles the result and sends that back to the application. So it can handle what we call targeted queries, where you say, I want the data for this customer, and let's say customer is part of the shard key. It says, oh, I know this customer lives on this shard, sends the data there, brings it back. The other type of queries are untargeted or scatter-gather. And that's where you say, I want to know about all the customers that bought this product and this range of dates that are from a state that starts with the letter M. And then MongoS says, okay, sends that query to every shard. Every shard runs that query locally, sends the results back to the sharding router. It assembles the results back together, sends it back to the application. Well, that's pretty cool. So now the goal is we keep adding shards, and you keep scaling things that way. Now, MongoS doesn't have to be our bottleneck, of course, because it's a very lightweight process, and we can have as many of them as we have app servers. They actually all know from the special configuration database which range lives where. And of course, talk about sharding can be its own special 2-hour session, so we're not going to go into much detail. But again, find me at lunch if you have any questions about that. Part of the goal that Dwight and Elliott had when they got started was that it would be easy to developers to get started with Mongo in terms of developing. But they also wanted it to be easy for developers to try things out in the real world, whether it be by provisioning a couple of nodes on Amazon or using a couple of machines they already have in the lab. So out of the box, the defaults tend to be reasonable, and I guess those of you who've tried it hopefully already know that. It's a little different in the real operational world, which we'll talk about more this afternoon. It's just a few little details. Hopefully you'll find all the different platforms that you like on there. There are no external software dependencies, so if I run it on my Mac, I run it on a Unix box, and we support drivers for over a dozen different languages, so hopefully that makes it easy to get started with in whatever language you use. There are many customers using this, and they're waving like I don't know that I'm 1 minute over. That's okay. I'll finish in 1 more minute. And actually, I have a lot more logos than that. If I was to talk about each one of them individually, we'd probably be here for the end of the day. So that's hopefully was not too much to take on all at once. We don't really have time for questions now, but maybe during the break and maybe at lunch. Thank you.